Our planet, Earth, is far more profound than it might initially appear. For millennia, humans saw planets merely as bright specks in the sky, no more than one-dimensional points wandering among countless, seemingly fixed stars. At that time, it was difficult to imagine Earth itself could be one of them. However, with the invention of the telescope, those celestial points transformed into entire worlds. Later, with the advent of spacecraft, they became tangible places. Earth, once thought to be a unique haven in the universe, was revealed as just one among many planets, each with its own distinctive features. Among the inner planets, the four smaller, denser, rocky worlds orbiting close to the Sun, Earth stands out as the largest. Its diameter is roughly 13,000 kilometers, and it possesses one large natural satellite, which we'll explore in greater detail shortly. Unlike the other three inner planets, Earth harbors something vital: water, and crucially, liquid water on its surface. Here, water can continuously cycle, flow, evaporate, form clouds, fall as rain, and mix with chemical elements to create astonishingly complex structures capable of sustaining life. Earth's ability to support life is inextricably linked to the presence of water, and, equally importantly, its atmosphere. Breathing, for instance, is a vital process, and, remarkably, both water and the atmosphere depend on Earth's magnetic field, which in turn arises from processes deep within our planet. Let's examine these in more detail. Like the Sun, Earth has a layered structure, with a core at its center composed of two parts, an inner and an outer core. The inner core is solid and primarily made of iron and nickel, heavy elements that sank toward the planet's center during its formation, allowing lighter elements like oxygen, silicon, and nitrogen to rise toward the surface. The solid inner core has a radius of approximately 1,200 kilometers, about 10% of Earth's total radius. The outer core, also mostly iron and nickel, is in a liquid state, allowing its components to flow. It is roughly 2,200 kilometers thick. Temperatures in Earth's core are extremely high, reaching about 5,500 degrees Celsius. Pressure is also immense, as expected, since it must support the weight of the entire planet. One might assume iron would melt at such temperatures, but it can remain solid under sufficiently high pressure. The pressure in the inner core is so great that despite the high temperature, iron stays solid. In the outer core, which is just as hot but under slightly lower pressure, the iron is liquid. Above the core lies the mantle, which is about 2,900 kilometers thick. The mantle's structure is unusual. Many imagine it as molten lava, but it's more like extremely thick, superheated plastic. While it behaves somewhat like a solid, over long, geologically significant timescales, it can flow. We'll return to this aspect shortly. Above the mantle is the outer crust, a solid, rocky layer. The crust's overall density is lower than that of the mantle, so it essentially floats on top. Earth has two types of crust: oceanic crust, about 5 kilometers thick, and continental crust, which is much thicker, ranging from 30 to 50 kilometers. Nevertheless, the crust remains thin compared to other layers. Importantly, it isn't a single continuous shell, but is broken into large tectonic plates capable of movement. This motion is driven by the flow of material in the mantle, which in turn is powered by heat. Earth's core heats the base of the mantle, triggering convection. Hotter material rises. However, this flow is extremely slow, only a few centimeters per year, so it takes roughly 50,000 to 60,000 years for molten material to move just 1 kilometer. As hot material rises toward the surface, the crust blocks its path. Magma pushes against the plates, causing them to drift very slowly, about as fast as your fingernails grow. But over millions of years, this motion accumulates, reshaping Earth's geography. Today, continents occupy positions vastly different from where they were millions of years ago. In some places where plates typically converge, the crust is weakened, allowing magma to break through and erupt as volcanoes. Other volcanoes, like those in Hawaii or the Canary Islands, are thought to result from plumes of hotter material rising straight through the middle of a tectonic plate. As the plate moves over this hotspot, a linear chain of volcanoes forms over millions of years. Volcanoes create new land as they erupt, but they also release gases from Earth's interior. In fact, volcanic activity played a major role in forming Earth's atmosphere. Earth's interior is so hot that its core is roughly as hot as the sun's surface. Where does this heat come from? Much of it is left over from Earth's formation about 4.5 billion years ago. As rocks and debris collided to form proto-Earth, their impacts generated heat. As Earth grew, its temperature increased, and its core remains extremely hot to this day. Additionally, as Earth's mass accumulated, gravity caused it to compress, and this pressure further raised internal temperatures. Another significant heat source is radioactive elements like uranium deep within Earth. They generate heat through the decay of their atoms. A fourth source involves dense materials, such as iron and nickel, sinking toward Earth's center during its formation. Their movement generated heat through friction. All these factors contribute significantly to Earth's internal temperature, which is why, even after billions of years, the interior remains molten. Earth's outer core consists of liquid, electrically conductive metal. As this fluid rises through convection, its motion generates magnetic fields, similar to how plasma on the sun creates its magnetic fields. Earth's rotation organizes this motion into giant cylindrical vortices aligned along the planet's axis. The combined effect produces a magnetic field resembling that of a bar magnet, with north and south magnetic poles located near Earth's actual rotational poles. These magnetic fields encircling Earth play a crucial role. They deflect the vast majority of charged particles in the solar wind and even trap some of them. Without this magnetic shield, the solar wind would directly strike Earth's atmosphere, gradually stripping it away over billions of years, much like a sandblaster removing paint from a wall. Mars, for example, lacks a strong magnetic field, and scientists believe this is why most of its atmosphere has disappeared. Yet Earth's atmosphere persists, and it's far more than just moving air. The atmosphere is a layer of gases above the crust. Since it isn't solid, It has no sharp boundary. Instead, it gradually thins with altitude. By convention, more a practical definition than a strict scientific one, the boundary between Earth's atmosphere and space is set at 100 kilometers. This is known as the Kármán line, and crossing it is generally considered the threshold of becoming an astronaut. By volume, the atmosphere is about 78% nitrogen, 21% oxygen, 1% argon, plus trace gases. It also contains water vapor. Most of these components are concentrated between 8 and 15 kilometers in altitude, with the lower part of this region being the warmest, driving convection that creates rising air currents. These carry moisture upward, forming clouds and ultimately producing weather. At around 25 kilometers altitude lies the ozone layer, composed of oxygen molecules that strongly absorb the sun's ultraviolet radiation, which can damage biological molecules. Thus, the ozone layer is vital for our protection. Interestingly, Earth's magnetic field not only deflects solar wind particles, but also channels some into the atmosphere, where they collide with air molecules at about 150 kilometers altitude. These collisions excite the molecules, which then emit light of various colors. Nitrogen glows red and blue, while oxygen emits red and green. This phenomenon is known as the aurora, visible near Earth's magnetic poles in the far north and south. The auroras can form stunning curtains and sheets shaped by the structure of the magnetic field. People may not notice the atmosphere until the wind blows, but it's always there. It exerts pressure on Earth's surface, about 1 kilogram per square centimeter, or roughly 10 tons per cubic meter. Right now, about a ton of air presses down on each of us. We don't feel it, however, because the pressure is applied equally from all directions, above, below, and sideways, and our bodies maintain internal pressure that balances it out. Earth also uniquely hosts liquid water on its surface, a feature that distinguishes it from other planets. Continental crust rises above oceanic crust, so water flows downhill, filling vast basins. About 70% of Earth's surface is covered by water. Some of this water likely formed during Earth's own creation, while some may have been delivered by comets and asteroids billions of years ago. The exact proportion of local versus extraterrestrial water remains a topic of scientific debate. Earlier, we noted that the atmosphere contains trace amounts of certain gases, one of which is carbon dioxide, making up only 0.04% of the lower atmosphere, yet playing an outsized role. Sunlight warms Earth, which then emits infrared radiation. If this heat could escape unimpeded into space, Earth would cool dramatically. But carbon dioxide absorbs this infrared radiation, preventing excessive cooling. This phenomenon, known as the greenhouse effect, keeps Earth warm. Without it, the planet's average temperature would drop below water's freezing point, turning Earth into an icy sphere. This is precisely why climate scientists are concerned about carbon dioxide. A small amount is beneficial, but too much can be extremely dangerous. Since the Industrial Revolution, human activity has added excessive amounts of this gas to the atmosphere, trapping more heat. All available measurements confirm that Earth's heat content is rising, disrupting the planet's balance. This is causing the melting of ice sheets in Antarctica and Greenland, as well as Arctic sea ice. Sea levels are rising, and excess atmospheric carbon dioxide is being absorbed by the oceans, making them more acidic. Science fiction has long featured the concept of terraforming, the idea of traveling to a hostile planet and transforming it into an Earth-like world. The reverse process doesn't yet have a name, but that's exactly what's unfolding on our planet today. Earth is the only known habitable world in the solar system, and its preservation has become our foremost responsibility. Today, we understand Earth as a planet with a scorching core, enveloped by a massive layer of semi-molten rock called the mantle, and capped by a thin crust. The liquid outer core generates a powerful magnetic field that shields the atmosphere from the solar wind, destructive force. Mantle movement drives volcanic activity, and much of the planet's surface is covered by oceans. The atmosphere is predominantly nitrogen, and its temperature is steadily rising due to human influence.